A very good afternoon to all the people who are connected with me here today. I'm Aanchal, a PhD student from Universitat Rovira Virgili in Tarragona, Spain. Today, I'm going to discuss some of the results from my PhD research work. The topic for today's presentation is Enhanced Gas Sensing Characteristics of Metal Doped Tungsten Disulfide Nanoflowers. This is the outline of my talk. I'm going to start with a brief introduction about ammonia and the importance of ammonia gas detection. This will be followed by properties of next generation material for gas sensing application. Then I'm going to discuss about the three-step gas sensing process which we have used for the synthesis of metal decorated tungsten disulfide nanoflowers. Moving on, I will discuss the gas sensing procedure used. Then I will show the results obtained where I will discuss the material characterization results followed by gas sensing results. Finally, to wrap up, I'm going to conclude with the conclusion and the future work required. Toxic gas such as ammonia is naturally present in the environment. It occurs as a colorless gas with a pungent smell. Although it is considered difficult to burn, it does pose the risk of explosion when stored under pressure and exposed to a high temperature ignition source. However, it is widely used in the production of many fertilizers, chemicals, food products, and in the pharmaceutical industry. It is considered toxic and corrosive to humans as it can damage skin, eye, and respiratory system, ultimately leading to death. Therefore, the acceptable concentration is 25 to 35 ppm. In this respect, for gas sensing applications, 2D layered nanomaterials analogous to graphene, such as transition metal dichalcogenides, have emerged as a promising material owing to their versatile characteristics, such as tunable band gap, high surface to volume ratio, inherent flexibility, low power consumption, and their high compatibility with conventional silicon technology. However, in spite of all of the above stated properties, pristine tungsten disulfide shows poor gas sensing response at room temperature. This is due to the strong adsorption of gas molecules on the tungsten disulfide surface, which leads to partial desorption of these gas molecules during the recovery cycle. One approach to improve the gas sensing performance of these gas sensors is decoration of the sensing layer with noble metals. This is due to the catalytic effect of the metal ions, which has a tendency to reduce the amount of energy required to react with gaseous molecules, resulting into improved sensing properties. Therefore, here we have synthesized tungsten disulfide decorated with different metal nanoparticles such as gold, silver, and palladium. The fabrication process of gas sensors involves a three-step procedure. The first step of deposition involves growing pure tungsten trioxide nanoneedles directly on commercial alumina substrate using tungsten hexacarbonide dissolved in a mixture of acetone and methanol. This is done using aerosol-assisted chemical vapor deposition technique. Figure A below demonstrates an image of the RCVD setup used. In the second step, the nanoneedles are sulfurized to form multi-layered nanosheets of tungsten disulfide in a quartz tube furnace employing atmospheric pressure CVD technique. For instance, figure B below shows a homemade CVD setup employed. In the final step, the as-grown material is functionalized with metal nanoparticles using the sputter deposition technique as shown in figure C. The sputtering parameters to deposit each metal nanoparticle differs in terms of the voltage applied and the deposition time used. In the next step, the fabricated sensors are tested for their gas sensing properties using a homemade gas sensing detection system. A typical illustration of the gas sensing process is demonstrated over here. The sensors were tested under a continuous gas flow in a Teflon test chamber that can accommodate 4 sensors simultaneously. The sensing measurements were done by monitoring the change in electrical resistance of the sensor upon exposure to ammonia gas. This was done by using an Herein multimeter. Also, a power supply source is used to change the operating temperature used. After the synthesis process, The as-grown material is characterized by different characterization techniques such as field emission scanning electron microscope, EDX, Raman, and XRD. FESEM analysis of pristine tungsten disulfide and tungsten disulfide nanoflowers decorated with metal with gold, silver, and palladium nanoparticles are shown over here. Tungsten trioxide nanoneedles sulfurized with the CVD process resulted in nanosheets of tungsten disulfide, which were randomly aligned to form tungsten disulfide nanoflowers. As shown in figure B, the nanoflowers were uniformly decorated with metal nanoparticles, such as in figure B, they were decorated with nanoparticles of silver. Next, they were characterized by Raman spectroscopy. The Raman spectrum of tungsten disulfide nanoflowers decorated with gold and silver nanoparticles is shown in the right side. From the spectrum, the two main Raman active modes for tungsten disulfide were found at 350 and 416. However, there is a shift in the peaks which could be associated with the addition of metal nanoparticles. Furthermore, we also characterize the samples using XRD and EDX techniques. The results of EDX are shown on the right side, where we can clearly observe the presence of gold in the gold decorated tungsten disulfide sample. The four graphs here shows the gas sensing characteristics of the three sensors towards different concentrations of ammonia gas at different operating temperatures. All the three sensors, when exposed to ammonia, shows an increased resistance, which indicates p-type semiconducting behavior. This is because ammonia is a reducing type of a gas. The response of the sensor is calculated using equation given over here, where R gas corresponds to resistance of the sensor in presence of ammonia, and R air corresponds to resistance of the sensor in presence of dry air. Figure A on the left-hand side demonstrates a bar graph presenting the response calculated for each sensor towards 10 ppm ammonia at three different temperatures. It is observed that the fabricated sensors shows different behavior depending on the operating temperature used. For instance, at room temperature, when the sensors are exposed to ammonia gas, the highest response is calculated with for silver decorated tungsten disulfide sensor. Whereas, as the temperature is further increased to 50 degrees, gold decorated tungsten disulfide dominates with a response of 18% as compared to the other two sensors. However, the highest response is recorded for palladium decorated tungsten disulfide sensor at 100 degrees with 23%. Similarly, figure B below shows the response trends of the three sensors as a function of varying gas concentrations of ammonia at 100 degrees Celsius. For this measurement, a diluted mixture of ammonia in dry air was injected in steps of increasing concentrations from 2 ppm to 10 ppm. Additionally, the two graphs on the right shows repeated response and recovery cycles for the three sensors at 100 degrees Celsius and at room temperature. Finally, to conclude, direct growth of tungsten disulfide nanofilms on the sensor transducer is achieved using CVD technique. This was followed by uniform decoration with gold, silver, and palladium nanoparticles via sputtering method. Finally, we have successfully fabricated chemoresistive gas sensors for ammonia gas sensing at low operating temperature. The results obtained demonstrates high sensing response of palladium doped tungsten disulfide sensor at 100 degrees Celsius, whereas at room temperature, silver doped tungsten disulfide sensor dominates the sensing response. Hence, these results indicate a possibility of fabricating inexpensive and energy-efficient ammonia gas sensors using palladium-decorated tungsten disulfide nanomaterial. Finally, in future, we would be studying the gas sensing characteristics of these sensors towards ammonia in humid environment and towards other gases. Also, we would conduct more research to understand the gas sensing mechanism with different metal doping. In the end, I would like to thank the research team in Tarragona and the funding that we have received for this research work. Thank you for your attention.